Entropy is a state function. That is an incredibly important aspect of thermodynamics. So S has to be a state function. So delta S can be or is equal to S final minus S initial, i.e. path independent. So what we're going to do is we're going to use the Carnot cycle to show that this is true. So here's the Carnot cycle where you have step 1, 2, 3, and 4, isotherm, adiabat, reversible expansion, adiabatic expansion, reversible compression, adiabatic compression. And you have steps, delta U, Q, and W, delta U, Q, and W, delta U, Q, W, da, 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 at each one of these that you add together. Okay, so if I had, let's say, some arbitrary cycle, pressure, volume, let's say it looked like this. So there's step 1, this is step 2, this is step 1. So let's say my first cycle goes here along this path, wonky, wonky, da, 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 and then the next path is this. What is the function? That function is PV equals nRT because it's reversible, which is great. This one is P over V, or P is proportional to 1 over V gamma. I can't remember the direct proportionality. But we know what these functions are, which is great. Well, I have no idea. And that's the problem. But what I can do is I can say, well, what if I have a whole bunch of Carnot cycles in the middle here? And let's say I put an infinite number such that I've pretty much put boxes. Okay, everywhere I put a circle is a Carnot cycle. So I can put 1,000,000 circles in here and have them be so small that they're essentially all canceling each other out here. So when one goes down here and the one goes back this way, it's canceling out this one because this one and this one are going to have the same work associated with them. Okay, everyone except one that doesn't have this edge or this edge or this edge or that edge. So what you can do is you can add up an infinitely small number of Carnot cycles until you really just get the perimeter. So you can approximate almost any thermodynamic cycle with adding together a bunch of teeny tiny little Carnot cycles. That's pretty cool. But what does that get for us? Well, what we're going to do is we're going to use that idea to show that entropy is a state function. Okay, for one cycle, we have an isotherm plus an adiabat plus an isotherm plus an adiabat. 1, 2, 3, 4. For this isotherm, we have the Q that we gain from the or the work put into the system per T. I'm going to call this Q1 divided by T1. Okay, plus Q2 divided by T2 plus Q3 divided by T3 plus Q4 divided by T4. All right, so this is the heat that's given off by this or put into the system per unit temperature that you're at. All right, but or not per unit, per temperature. So there's a certain amount of heat that's put in the hot reservoir, but then there's also a certain heat that you have at the cold reservoir. So we want to say, well, what is the normalized, if you will, heat that we have per that particular temperature? Well, but for the adiabats, what is Q? 0. Well, that's great. So Q1 over T1, and this is going to be the hot temperature, and then this is going to be the cold temperature. You're going to have then all of the isotherms are going to be the ones that are contributing this Q per T. Okay, and so like I said over here, we're going to sum up all of the different cycles and what they're contributing, but the adiabats aren't contributing anything in terms of this Q per T value. So then what we can do is we can say, well, I've got the sum of all 4 of those cycles, where I is equal to my first one, of Qi divided by Ti. Okay? Okay, so now if I have, essentially, I'm adding an infinite number of my Carnot cycles around, and I'm looking at the amount of heat that I get from each portion of the cycle divided by the temperature of that isotherm, then that's going to say, well, that's going to really give me the heat associated with this path, right? So if I now have the heat associated with the path, I can then say that's essentially equal to the path integral dq reversible over T. Now, the only way I can make this a dq where it is an exact differential, not an inexact differential, is if I take the path integral. But I need to know the path associated with that. Well, but in the limit of infinitesimally small Carnot cycles, you essentially then have this becoming an infinitesimal or an exact differential. And so what we can do now is we can say, well, you know what? I'm going to define entropy. S is equal to dq reversible over T. And if I do that, and I take the integral of this then, and so I can say, all right, well then ds is equal to the integral of dq reversible over T. That means that I get a delta S associated with from state 1 to state 2. So I get S2 minus S1, which tells me that entropy is a state function. Sweet. If and only if I have this defined as ds is equal to dq reversible. And knowing that at this point, I don't have a path function associated with my dq, so that's why I have to have this little hat here, because this is the path integral. But under the assumption that this becomes infinitesimally small such that I can determine what the path is it becomes dq. So what do you do with this? Well, you use the fact that the definition of entropy, S, is equal to dq reversible over T. This is your start of entropy, all right? And it's using the idea behind the Carnot cycle that helps us create the fact that this side of the equation is a state function. This side may or may not be one, depending on what assumptions that we're making and how we're just constructing our system. Yay, entropy.